So the material world is a pretty mixed up place. Literally, most of the substances that you're going to interact with are actually mixtures, not pure components. The air you breathe, that's a mixture. Even the water that you drink is a mixture. It has trace amounts of chlorine and fluoride in it to help your teeth, and other compounds as well, and trace levels. So a lot of things that we think of as being, nice and pure really have some other stuff mixed in. So as chemists, we might be interested in separating those into their pure components. That way we can help to identify what the different pure components are, let's say. So how do we separate things? Well, we separate things by using physical processes. So we're going to talk about physical and chemical processes a little bit later, but we're going to use physical processes to do that. So that's something that you could do sort of mechanically without changing the chemical identity of the substances involved. So how do we do that? Well, we're going to make use of differences in physical and chemical properties. Well, I just talked about physical, so really mostly physical properties that we're looking at. So some examples of these ways of separating things: filtration, centrifugation, which involves a process called sedimentation, which takes place naturally. That's how we get sedimentary soils, for example, sedimentary rocks. Chromatography is a very important modern method for separating things, and distillation has a very long history in the brewing industry, but it's important for separating liquid mixtures as well. So let's look at some of these. So in your textbook, they talk about, let's say you've gone out and you found this bloom of algae in the ocean somewhere. So you're going to collect some of this phytoplankton, this sample, and you want to sort of study the phytoplankton. You want to look at some of the pigments that might be involved in the phytoplankton, the different types of chlorophylls that are responsible for absorbing the sunlight. So you have this sample here in your flask, and what you're going to do is filter that. So filtration works on the basis of size. So some of the particle matter is too large to pass through pores in some sort of filter material. In this case, we've got a funnel right here. This is called a Buchner funnel, and there's a piece of filter paper in the bottom, and then there's a suction flask right here. So we pour the liquid on. The larger phytoplanktons will stay on the surface. The salt water, the seawater, some of the other small molecules will be able to get through the pores on the filter paper and drip into the flask. We can even lower the pressure in this flask by connecting this to a vacuum, and since there's lower pressure here, the atmospheric pressure pushing down will actually force the liquid through the filter paper, which speeds the process up a little bit. So this is called vacuum filtration. Now you will have separated out a lot of the phytoplankton particles, the algae that you want to look at, and so now maybe we want to do something else. We want to extract some of those pigments from the phytoplankton. Well, how might we do that? Well, we scrape the filter paper off and we put it in a test tube. And then we're going to use some solvent. In this case, they're using acetone. This is called solvent extraction. So you choose the right kind of solvent, it will dissolve some of the material and leave other material behind. So choosing the right solvent can help you separate mixtures. Again, the principle behind this separation, the physical basis of this separation, is differential solubility. Some things dissolve and some things don't. This is, for example, how you might separate a mixture of salt and sand. So you've got little salt particles and sand particles, and sure, you could get a microscope and tweezers and go in and separate it grain by grain, but man, who wants to do that? So what you're going to do is you're going to take a big thing of water, dump that in with the salt-sand mixture, shake it up, the salt will all dissolve in the water, and then you can pour that off or filter off the sand, and then you've got the sand. Now, if you really want the salt, how do you get that back out of the water? Well, that would be a different process. So we're going to have to evaporate the solvent somehow to get that away from the salt. So anyway, both of those processes are examples of solvent extraction, using differential solubility, the ability to dissolve differently in different materials. The next process would be centrifugation. So this method actually uses differences in density. So in centrifugation, you take a tube that contains your sample material and you put it inside a rotor that can spin very, very fast. So your test tubes are now fixed in here, and this rotor is going to spin around very fast. Fancy machines can actually refrigerate things and change the atmosphere inside. So these spin very, very fast, and so that creates a lot of centrifugal force to the outside. So the larger, more dense particles are going to move that way because they feel a larger centrifugal force, so there's a greater force. The less dense materials will then pack in up here. Some fancy centrifuges have swing arm rotors so that as it swings, these little test tubes swing outwards, and then you get a big force that's going to pack everything down here. And so this might be a good way to remove lots of cellular material if you wanted to get all that cellular material out of the way and keep some of the smaller molecules up here, and then you could pipette them off, or maybe you want to analyze this stuff. Either way. Some types of centrifugation actually work by putting layers of different density in here, and then your molecules will actually form little bands in your test tube, and you can stick a pipette tip in there and suck out the band that you want. This technique is very, very important. It's chromatography. And the physical principle behind chromatography, the physical principle of that separation, has to do with differences in solubility and adsorption to some sort of solid material. So we look at those sorts of differences. This is an example of something called thin layer chromatography, or TLC for short. So in this example, what we do is we get either a piece of paper or a thin little plate that has a coating of a porous material on top. Typically chemists use silica for that, or alumina. And then what we're going to do is draw a little pencil line right on the surface here. We're going to take our sample of solvent extracted phytoplankton and make a little drop. In this case, we've made a big long band. And then we're going to take that piece of paper and stand it upright and dip it into a beaker of solvent so that the solvent level comes kind of way down here and doesn't touch this line. Now this material, this paper or this silica on this thin layer, is porous. So by capillary action, that solvent will start to move through the pores and it's going to move up this paper. You've seen that if you've ever put a drop of water on a paper, it will gradually spread out as it moves through the paper. Now what happens when it hits your sample up here? Some of the sample material will dissolve in that solvent. And as it moves up, some of that sample material may be slowed down because it interacts with the paper a little bit, or your layer. And so as things move up, some move quickly with the solvents, others slow down, and it's a way of separating out all of your components. So here you could see perhaps the different pigments that are in your phytoplankton. There are even ways of kind of scraping your sample off carefully and then doing something else with them. We can also do a different type of chromatography where we take a tube, a column, and we pack it with this material, and then we run our sample from top to bottom with the solvent. The same thing is going to happen as they move down a tube. They're going to separate into these different bands, and then you can open a spigot at the bottom and one by one collect the different bands as they come out of the bottom. So chromatography is a very, very important separation method in modern science. In fact, there's an area of analytical chemistry called separation science, and most of those folks are chromatographers. Here's another way that we could separate things. Remember I talked about that salt-sand mixture, and then we had this problem that now we've got salt water, and maybe we want to get the salt out by itself or the water out by itself. So imagine that instead of working with phytoplankton, that again you're at sea, but now you're stranded at sea, and well, you're going to get pretty thirsty because, like they say in the rhyme of the Ancient Mariner, water, water everywhere, but nary a drop to drink. Yeah, so you can't drink seawater because you'll get sick. So what do? Well, this little device works through distillation to purify the water. So distillation is a way of separating liquid mixtures. The physical basis of that separation is differences in boiling point. So in this case, we've got salt water. At a molecular level, we've got water molecules, little gray guys in here, and salt, which is made of sodium and chlorine as ions. So a sodium cation and a chlorine anion. We'll learn more about those things later. In any case, the water is able to boil at a much lower boiling point than, say, sodium chloride. So in this little device, what happens is the sun, through the greenhouse effect, heats up the air inside here. That's going to cause more of the water to evaporate. Even though the air is warm inside here, the outer layer is probably relatively cool. It'll be more the temperature of the outside air, and so the water condenses on that outside surface and then drips down into this little lip right here, and then there's a siphon tube right here that you can use to actually drink that water. So that water would then be suitable for drinking. So you can go from seawater to drinking water, and that's pretty useful. So that's a distillation process. Now in a lab, a distillation apparatus might look a little more like this. In this case, we've got some sort of liquid mixture that we want to separate. We put it on a hot plate, we heat it up. The more volatile components, those that are more easily converted into a vapor, will boil off first. They boil off, turn into gas, and then they hit this apparatus over here. This is called a condenser. What it is it has a thin tube that goes all the way through, and then around that we're going to wrap another tube that has a couple of these little side arms on it, and we can flow water through that tube. So we can make that inner tube cold by flowing cold water through that. So these vapors are going to hit the cold water, and they're going to form little droplets, condense, and then drip out here. And hopefully they will be more pure in the low boiling component than the other components. And this process gets used both in the petroleum industry. This is how we take crude oil and convert it into things like gasoline and turpentine and all of those things that you might want to use for cleaning or running your car. But this is also in the beverage industry, the adult beverage industry, historically how you take beverages that have low alcohol content and convert them into beverages that have higher alcohol content. So we do that through a process of distillation, and moonshiners know about this process well. So that's another great way of separating liquid mixtures, in this case, based on differences in boiling point.